The next type of interrupt I'd like to look at are called INT interrupts. Now, INT interrupts are interrupts which interrupt on edges. You have three INT interrupts with the PIC processor, INT 0, 1, and 2. Each of those can interrupt on the rising edge or falling edge of a signal on port B pin 0, 1, and 2 respectively. What you can do with INT interrupts is it's a more efficient way of responding to buttons being pushed. A couple examples of what you can do with INT. First, to set up the interrupts. Like all interrupts, I have to make the input pin input. I have to set the conditions for the interrupt, which for an edge interrupt is either the rising edge or falling edge, not that many options. I have to enable the interrupt and do a global interrupt enable. If I do that, then every rising edge or falling edge I call an interrupt. A couple examples. Let's do a voting machine. Suppose I have three candidates running and I want to have a machine count how many votes for candidate A, B, and C. I can do that with INT interrupts. What I'll do is essentially have four programs running in parallel. I've got the main routine that sets up the interrupts. Then in parallel, I've got the three interrupt service routines. Those are fairly simple programs. All they do is, when the interrupt is called, add one vote for the appropriate candidate. The program is fairly simple. I've got my three interrupt service routines. If I have an interrupt on port B pin 0, 1, or 2, I simply increment the appropriate counter. In the main routine, I have to enable each of the interrupts for rising edge. And then in the main loop, all I do is display how many votes for each candidate. What that looks like is the following. I start out 0 votes for each candidate. When I hit RB0, I get 1 vote for candidate A for each button. RB1, I get 1 vote for each candidate, or for each button push. Likewise for candidate C. The limit on this program, it takes about 50 clocks to trigger an interrupt. I can only have 1 vote every 5 microseconds, or about 200,000 votes per second. So if I hit fast enough, I'd have to hit the button over 200,000 times a second for the processor not to keep up. That's one example of INT interrupt. Second example, let's measure the time that a button was being pushed. What I'll do is I'll have timer 0, keeping track of time, 200 nanoseconds, then INT 0. Every time I hit the button, I just record the time that the button was being pushed, save that in variable T0, then display T0. What that looks like is this. I've got timer 0 displaying time, 200 nanoseconds, on the top row. The time of the button pushed is displayed on the second row. There I hit the button at 14.4327911 seconds. Actually, this time is a little bit off. It takes about 50 clocks to trigger an interrupt. So the time that's displayed is about 50 clocks after the time I hit the button. I can get more accurate, but that'll be tomorrow's lecture on timer 1 capture. Here I've got the precision of 100 nanoseconds, but the accuracy, I'm off by about 50 clocks. Third thing you can do with INT interrupts, I can generate random numbers. Here the idea is I'll have timer 0 running in the background, keeping track of time to 100 nanoseconds. The time that I hit the button, mod 6, will be my random number generator. What that looks like is this. I've got time running in the background, that's the top row. Every time I hit RB0, the time mod 6 is my die roll. So there was a 3, another 3, 1, 5, 3, 6, 1. And one way to generate a random number. Finally, one last example of what you can do with INT interrupts. I can interface optical encoders or digital potentiometers to a microprocessor. What a digital potentiometer does is as you turn it, it outputs a square wave, usually 2 of them, A and B. What that does, if I count edges, that tells me how far I've turned. For direction, I have the second one. For example, if I'm going left to right, on the rising edge of A, B is low, that's at the circles. If we go the opposite direction, on the squares, now the rising edge, B is high, so I've got distance and direction from the phase quadrature encoders. In terms of coding, what I'll do is use 2 interrupts, A and B, actually just 1 interrupt in B. One version is to simply have an INT 0 interrupt on the rising edge. I just check, what's on B1? If it's positive, I'll add 1. If it's negative, I'll subtract 1. What that looks like is this. I have an optical encoder connected down there. As I turn the knob, notice that port C, pin 0 and 1. If I turn it clockwise, it goes 0, 1, 0, 1. If I go counterclockwise, it goes 1, 0, 1, 0. So there's your distance and direction. Which one comes first? Bit 0 or 1? Currently it's not reading because there's too much loading on port B. The LEDs are pretty, but they draw too much current. If I pull the jumper out, the LEDs no longer work on port B, but now I have enough voltage for it to see. So as I turn clockwise, that's the negative direction. I count backwards. Turn counterclockwise, I'm counting up. If I turn all the way around, here's one rotation. Right there. This encoder has 128 counts per rotation. Here's 2 rotations, 3 rotations clockwise, going counterclockwise. This is actually what the knobs look like on most of the oscilloscopes in lab. I can sit there and spin them as often as you want, as far as you want. And the microprocessor is just keeping track of am I increasing or decreasing a number. That can tell you the frequency, volume, whatever it is the microprocessor is using that input for. So that's a couple examples of what you can do with INT interrupts.